Hello and welcome. Today I would like to continue the repair work on this Packard Bell PB430 mainboard. If you saw my last video, you will probably remember that after a repair of a heavy damage due to a leaky battery, this board booted properly and everything worked fine, except that the board was very slow. Like if it would run with deactivated turbo, but switching the turbo mode didn't change anything. I wasn't sure if it was related to the turbo functionality at all, but since I didn't have any schematics or chipset documentation for this board, I was a little bit lost and didn't know where to start. Luckily, one generous viewer of my channel donated another very similar board to me, Packard Bell PB430, which also was in a very bad condition and needed a lot of work to get back to life. I was hoping that if I would be able to repair it, this board would give me some hints what could be wrong with the PB430. And this was what I did. With quite a lot of effort, I brought it back to life. However, this PB410 board was running at full speed all the time, and now I couldn't deactivate the turbo mode. So I got two very similar boards, one where turbo didn't turn on and another where turbo didn't turn off. And in this video I would like to take a closer look at these boards and find out what's going on. Well, it needs to be told that it was only my assumption that the issue had something to do with the turbo functionality. That's why I made a lot of measurements off camera to exclude all kind of other possible issues, and to be honest, I didn't find anything suspicious. Of course, I triple checked all the jumpers and played with different settings, but that didn't change anything. The BIOS settings on this board are quite rudimentary. There is an option to enable or disable the cache, and that setting didn't have any effect. And that is basically it. On the second page there are no related options at all. My best guess remained unchanged so far, but I needed more hints that it really had something to do with turbo. And before I continue, I would like to answer the question what that turbo actually was. Well, as the 286 and 386 CPUs were introduced, there was still quite a lot of software which was implemented for the good old IBM PC XT and compatible machines which were running at 4.77 MHz. As programmers developed their software back then, they considered that frequency to be a system constant which would never change. A lot of games and other software were hard-coded for that 4.77 MHz CPUs. And as then IBM introduced its PC AT with a 286 CPU running at 8 MHz, all that old software suddenly started to run too fast, and that issue grew of course with higher clocks of later 286 and 386 CPUs. Computer manufacturers, of course, didn't want to displease their customers by enforcing them to throw away their expensive software and introduced a mechanism with a button on the case which would slow down the CPU so much that the old software would be usable again. However, marketing didn't want to see a button with name slow on their computers, and instead they named it turbo to show that the computer runs in turbo all the time, but can be set in deturbo mode by pressing that button. So eventually turbo didn't make your computer run faster, it actually made it run slower. As I mentioned in my last video, the turbo functionality is a different story on every board. There is no real standard how this has to be made, but so far I saw three common ways of implementation. First one is obviously the CPU clock manipulation. Here, for example, this 386 mainboard, which you maybe remember from an old overclocking video. This board has a soldered 386SX CPU on board, which runs at 16 MHz. The CPU requires a clock which is twice as high as the specified CPU clock. It is divided by 2 internally to generate the internal processor clock used for instruction execution. The related input is called CLK2 and is located at pin 15. And as you can see here, we have 32 MHz external clock indeed, and the CPU should run at 16 MHz internally. Now let's see what happens if I press the turbo button to set the system into slow deturbo mode. The external clock dropped by half and is now 16 MHz, or 8 MHz internal CPU clock. And the landmark speed test confirms the speed drop. Another way of slowing down the CPU was the usage of so-called hold signals, which told the CPU to step back and give control to another devices. Without going into details, by emitting the hold signal of particular length and frequency, the CPU could be enforced to wait every now and then and obviously run slower. Starting with 386DX, caches were added to the CPUs and another way of slowing down was introduced. Usually, in addition to holding the CPU for a while, also caches were deactivated in deturbo mode. This solution was usually used on the 486 and early Pentium CPUs, after which turbo feature was considered to be not required anymore. And with this knowledge in mind, let's continue with the investigation. As I said, I made quite a lot of measurements and tests off camera, played with jumpers, tried to switch turbo with various software utilities, but with no results. PB430 board ran very slow and PB410 ran at normal speed but couldn't slow down. First I concentrated on the PB430 and there in speedsees I could clearly see that there was no cache whatsoever. The Intel 486SX has 8 KB of internal level 1 cache and we should have seen a bump in the beginning. However, there was a flat line over the whole length and it took forever to finish these tests. Cache check confirmed that results and reported no cache as well. As I already said, I also tried to enable and disable the cache in the BIOS, but I also inserted 128K external level 2 cache ICs to see if something changes. All that didn't change anything. The system remained slow and no cache was reported. So at this point my assumption was that the cache is somehow involved into the turbo functionality. But it couldn't be only that, since the system was much slower than a usual 486SX33 with deactivated cache. One important thing to mention was the sound of turbo switching. As I showed in my last video, this PC has no turbo button, but it has a turbo LED and the turbo functionality can be switched by pressing Ctrl-Alt+ for turbo on and Ctrl-Alt- for turbo off. So when I switched the turbo mode on the PB430 mainboard, I could clearly hear high-pitched beep for turbo on and low-pitched beep for turbo off. However, the LED didn't switch and remained always green. To compare, if I switched turbo on the PB410 mainboard, I heard the same sound, but in addition to that, the LED light also turned yellow every time I switched turbo off. So the system definitely seemed to react to turbo switching. It just didn't change the mode, but only notified the status. Okay, so what actually happens if we press Ctrl-Alt+ or minus on the keyboard? Well, due to some design limitations of the early x86 systems, the keyboard controller was used for all kind of creative quirks. Also, the key combination to switch turbo mode was usually handled directly by the keyboard controller, which notified some turbo switching circuitry in the mainboard. It could be some dedicated logic or integrated directly into the chipset. How exactly this had to be made, which circuit handled that signal, and how the keyboard controller firmware had to be implemented was up to the mainboard manufacturer. Yes, keyboard controller is eventually also just a microcontroller and the firmware can vary from board to board. So, on this board I had an option to find out which pin on the microcontroller would notify the turbo mode change and follow the traces. However, as I searched the documentation for the PB410 mainboard, I stumbled upon this page, which showed the front panel connector pin out. Remember that this computer has no physical turbo button. Nonetheless, it turned out that there is a pin on the board where such a button could be connected. If this pin is connected to the ground, the system should switch into deturbo modes. Of course, I tried it, but once again with no effect. Neither PB430 board nor PB410 showed any reaction. But the good news was that I didn't have to analyze the keyboard controller anymore, since I had my pin with a coordinate trace which I had to follow. After some research, I found that the trace from the pin header was going to this inverter and afterwards into this programmable array logic IC, PAL16R8, which was dangerously near to the area damaged by the leaky battery. Before I continue, let me briefly explain what such a PAL actually is. In short, it is a logic IC which emits some output dependent on the input. This IC is programmable and what it does is highly dependent on the program which was written on such an IC. It can be quite complicated because it can work in different modes and it can replace quite a lot of discrete logic ICs, what means it saves a lot of money for the manufacturers, hence it is quite popular. I use such an IC in my MCE to VGA and CMS projects, as well as in some others which I didn't announce yet, so I have quite a lot of experience with such chips. The problem is that if such a chip goes bad, it can be quite hard to replace it. As I said, those chips were programmed with some proprietary code by manufacturers of the hardware and is nothing what you can buy from the shelf. The only way to go is to reverse engineer the functionality and write your own firmware. So I measured once again directly on the PAL if the input changes whenever I switch the turbo mode. And as it did, I followed the logical conclusion that something on the output of that PAL has to change as well. I looked through all of the output pins, and although I did find some output, none of that did ever change dependent from the turbo switch on the input. What I found interesting is that one of the inputs got 12 MHz, and on some of the outputs other frequencies were generated. Almost 6 MHz, slightly more than 3 MHz, around 1.3 MHz and about 650 kHz. Each next value was nearly divided by 2, but the values on the PB430 were quite unstable and not quite on point. So I measured those on the PB410, and there every next value was always exactly halved. I could measure the same 12 MHz input and divided output values of 6 MHz, 3 MHz, 1.5 MHz and 750 kHz. One output, however, caught my eyes. This output pin emitted impulses with over 600 kHz on the PB430, where it stayed always high on the PB410. So I followed the traces and bingo! It went directly to the CPU, in particular to the pin C15 flush. And what does the documentation say about that pin? Cache flush, input pin active low. The documentation distinguishes between write back and write through modes, but essentially it tells that it enforces the CPU to invalidate its caches. The signal is low active, and as you see, the PAL keeps it low for a longer period of time than high. The CPU can't continue its work as long as the flash is low, and so it is not only forced to drop the cache, but it is also blocked for a longer period of time. The CPU gets about 200 microseconds every 1.6 milliseconds to get its job done, and all the other time it flushes the cache and waits. That would mean about the 1/8 of performance, and if we compare the results of PB430 and PB410 with 17 versus 158 points, that would be about right. As a final evidence, I decided to solder a wire to 5V rail on the board and connect it directly to the named PAL IC output pin and override it with high value all the time. And would you look at that? As soon as I touched the PAL output with 5V wire, the mainboard went instantly into turbo mode. Now I needed to reverse engineer that PAL IC, so I followed the other traces from it, and this was what I found. Pin 1 is 12 MHz clock, which comes from the clock generator. Pin 2, 3 and 4 are connected to the CPU clock selection jumpers. Pin 5 goes to the keyboard controller. This is the one which notifies the Control Alt plus and minus turbo switching on the keyboard. Pin 6 goes to the chipset and seems to be always low. Pin 8 goes to the turbo button through an inverter, as I mentioned before. Other input pins are pulled low. Now to the interesting side, outputs. Of course, those are open to interpretation. Since both of my mainboards seem not to work properly, all I could do is to measure the outputs on both boards and try to make a conclusion. As I said, pin 12 is the one which goes to flush input of the CPU. The pins 13 through 19 seem not to be connected to anything, but are used by the PAL as I/O pins itself. For example, it takes the 12 MHz pulses from the input pin 1 and generates 6 MHz on the pin 17. Then it takes the pin 17 as an input again and generates 3 MHz on the pin 16, and so on. Pin 19 is a cumulative value of the turbo switch, which takes the values from the turbo button and the keyboard's controller into account. Eventually, using all those values, the output on pin 12 is generated roughly as we saw it on the oscilloscope. If the machine is set into deturbo mode by pressing the turbo button or using the keyboard, the flush signal is generated frequently. When in turbo, the output is high all the time and the CPU is not forced to flush the cache or wait. I will not go into details of the implementation, but with all the information which I could gain from those two mainboards, I could create a firmware, but I needed to test it somehow. The PAL 16R8 ICs, like the one which was soldered on these Packard Bell mainboards, are one-time writable, but there are replacements for those made by Atmel, for example, under the name ATF16V8, which are rewritable. There are some slight differences which are not interesting now, and the Atmel IC is good enough replacement. These ICs are made in different packages, and on the board we need a PLCC, but for experiments I took one in a DIP package. I burned the firmware on the chip, and here is the setup on the breadboard which I used to test it. Here is the clock generator, similar like the one on the mainboard, and which delivers 12 MHz clock as we need it. And as you see, the input clock is generated properly. Now this button here represents a turbo signal which comes from the keyboard controller. As you see, it goes low as soon as I press it. Here we have our 6 MHz. Doesn't look as nice as 12 MHz, but good enough for a breadboard without additional capacitors. Here we have 3 MHz. Here are 1.5 MHz. And here we have 750 MHz. These are flash impulses, as we would need them prepared on another pin. And this pin is the actual flash request output, which would go to the CPU. As you see, it is high all the time because the turbo button is not pressed and the system should work at full speed now. And if I press the deturbo button, we suddenly will see a very similar graph shape as what we have seen on the PB430 all the time, independent from the state of the turbo button. And after I had a working prototype, it was time to desolder the PAL from the board. As I removed the IC, I thought that without it, this board should be able to run in full speed, since there would be nothing what would generate the flash signal for the CPU. Without the PAL, the flash signal would be always high and the CPU would run as fast as it goes. And as you see, that was indeed the case. Of course, now turbo couldn't be switched off anymore. I wanted to check the desoldered chip in my test setup, but it turned out that the IC was now completely dead. The input was fine, but no output was generated. I don't really know what happened, but maybe the already damaged IC completely gave up under the higher temperature. Rest in peace, old pal. I didn't want to solder the IC on the board on the first try, because I was afraid that I'd need to desolder it again in case of a mistake in the firmware. So for easier testing, I soldered a couple of wires to the required pads on the mainboard and soldered the other ends to a DIP socket so I could test my solution. And as I restarted the system and pressed Ctrl-Alt+ and minus on the keyboard, I could see how the LED color started to change. If you remember, this worked on the PB410 boards, but on this PB430 it didn't work at all, so it was a good sign. But the final relief after all this journey I had as I finally was able to switch the turbo mode in the landmark speed test. Also in sysinfo that worked just fine. And SpeedSys and Cache Check now also confirmed working level 1 CPU cache. After I tested the prototype, everything what has been left is to write the firmware on a PLCC chip and solder it to the board. And this is it. I still have to apply this fix to the PB410 board, but the PB430 now is working at full speed and can be properly slowed down if needed. By the way, Doom is now playable as well, though this system has some potential for improvement, but this is a topic for the next video. I didn't publish my reverse engineered firmware anyway yet, but if you need that, give me a note in the comments. Maybe this is something what we should archive in the RetroWeb project? We will see. And I hope that this deep dive into turbo functionality and the repair was interesting for you. Please let me know in the comments what you think about it. Give me your thumbs up if you liked it, or down if not. And in the next video I will probably continue to restore this machine, maybe do some upgrades, a little bit of hard drive archaeology, benchmarks and gaming. So far, thank you for watching and goodbye.